Hello, my name is Matthew Cunha. I am presenting my team's project of an electromechanical design of a vacuum chamber with vibration and noise dampening capabilities on an autonomous undersea vehicle, an AUV. This project was done at Wentworth Institute of Technology as our capstone project. The project was done in conjunction with the Naval Undersea Warfare Center, Division Newport. Review of the AUV project. The project was designed and developed at Newark Division Newport. The project was given to two schools, Roger Williams University and Wentworth Institute of Technology. The two teams were tasked with designing an AUV that would start in the start-stop semicircle. It would go down a pool lane where halfway down the pool lane there would be two detecting hydrophones and an imaginary choke point. The hydrophones would detect the noise that would be radiating from the autonomous undersea vehicle. And as it passed through the imaginary choke point, the communication station would be reached where the AUV would send a Morse code signal out to the communication station. The communication station would receive the code. If the code was correct, it would give a signal back saying that the code is correct. AUV would turn around, go through the imaginary choke point again, where a sound reading would be taken again for accuracy, and go back to the start-finish semicircle. Continuing with review of the project, each school was given a black box noisemaker, where inside of the black box noisemaker were two offset rotating masses and a fire alarm. This is where the main sound came from and where each school was tasked with quieting the black box, and whatever school quieted the black box the most won the competition. For fundraising, my school raised a total of $3,295 through generous donations of GoFundMe. These donations came from friends, families, and organizations. Going through our design iterations in the engineering design process, we came up with 4 viable designs that we thought were probable. Through simulations and further testing, we came up with our final design, which can be seen here. This was taken during one of our testing sessions at Simmons Pool. Simmons Pool is very gracious enough to let us use their testing site weekly for our AUV during hours where they were not using it. They were very generous. Our final design contained an acrylic box, stabilizers, 3 sonars, 2 thrusters, a vacuum chamber where the black box was held, a keel for stabilization, the rear hatch, speakers, hydrophone, and a nose cone, all for the communication station. Our AUV was controlled by the Jetson Nano, and it ran on Ubuntu 20.04 as its operating system. The Jetson controlled the thrusters, sonars, and the communication station. All of the data transmission for the Jetsons runs on ROS and Python. ROS is the robot operating system. The Jetson used both GPIO ports and USB serial ports that were utilized. The Nano runs on all processes of all autonomy on the system. So the Jetson Nano ran all of our autonomy and kept everything going. ROS2, we used Foxy Fitzroy for our ROS. Foxy uses Ubuntu on the Jetson Nano. It uses both Python codes for basic things such as thrusters on and off. ROS will also use for simulation operation, which is necessary for AI/autonomy. ROS is not a coding language to specify. It is more like working in an environment. For the electronics, we came up with a pretty simple system that ran off a Milwaukee 18-volt battery pack that we modified and ran all of our systems on it. We had 2 different electrical systems. We had an 18-volt system and a 5-volt system and a control system. The power systems all came from the battery, then ran for the 5-volt system, ran into a 5-volt regulator that created all the power we needed for the 5-volt system. The 5-volt system would power the Jetson and the 3 sonars. The 18-volt system ran directly to the 2 thrusters. For the autonomy, we used ROS, like I stated before, and the autonomy worked in conjunction with the sonar, which came out as a 30-degree cone shape with an effective range. It had 50 meters of effective distance, and it kept the AUV centered in the lane. So to keep the AUV in the center of the lane, we took readings from both sides of the AUV. If both sides measured the same distance, the AUV was in the middle of the lane. If the distances were off, then the AUV would correct using the sonar and thrusters. As you can see with the flow chart up above, you can see what our priorities were for moving straight, turning right, and turning around, and turning left. The main body was made out of acrylic that we laser cut at Wentworth. We used kind of like dovetail grooves to make the gluing process easier and make sure that we had a very good seal. For stabilization and buoyancy, we used a steel keel and a flotation device on top for buoyancy. This allowed for us to get a very heavy weight at the bottom because our AUV was full of air. So the keel created weight that would keep us down, and the buoyancy on top allowed us to stay right where we wanted to. Sealing, to keep the water out, we used ABS plastic for the main hatches that we sealed using Plastidip and silicone. Continuing with the silicone, we put all edges filled with silicone around the dovetail grooves to add an extra layer. Sound dampening was the main aspect of this project, and we used a vacuum chamber that the black box noisemaker fit into. You can see the acrylic vacuum chamber with cones there that kept the black box off the acrylic, which did not allow for the vibrations to transfer that well to the outside body and out into the water where the sound reading would take place. Continuing with the vacuum chamber was hooked up to a vacuum pump where we pulled air out of the black box area, which allowed for very little sound to pass through because that sound cannot pass through a vacuum. The communication station, as pictured there, contained a hydrophone and a speaker. The hydrophone would listen for the sound from the communication station, and after the Morse code was processed, it would be blasted through the speaker. For our testing, we did vacuum chamber testing from February to March. We did water testing from March to May, every Monday and Wednesday at Simmons Pool from 8:30 to 10:30, which we were very thankful for. Continuing with our testing, our main objectives was pull the vacuum and measure the effectiveness of the design. And for water testing, we needed no leaks, we needed to get the autonomy working, and we needed our buoyancy. Vacuum chamber testing came out to show that our outside the vacuum chamber decibel reading came out to 84.7 decibels. When the black box was inside the vacuum chamber, the decibels dropped down to 60.8. When the black box was inside the vacuum chamber with a vacuum inside the AUV, it dropped down to 43.9. And then the ambient noise without the black box just in the room was 37.3 decibels. For our project, like I said, we raised money through GoFundMe and through all of these generous companies, organizations, and just friends of ours. We were able to complete this project. Thank you.